Hi everyone, welcome to the Software Development Essentials Workshop and the second of 5 total classes. This class is the first of a 2-part series called the Full Stack Developer and focuses on the front end. The next class will focus on the back end. This class is geared towards the following audience: entrepreneurs who are looking to build a software-backed product, professionals who either already find themselves in the technology space or are looking to break into it, students who are looking to learn some material they might not get in the classroom, and curious individuals who just want to understand more about how the modern world is being built. The objective of this class is to understand the internet, the various layers of the stack, and the design and the components of the user-facing presentation layer, otherwise known as the front end. Here's our agenda for the day. We're going to first cover the internet itself, how it works, what are its components. Then we're going to define the stack, and then we're going to proceed into one half of the stack, the front end. We're then going to zoom out a bit and talk about design patterns and design thinking. And finally, after the lecture, there will be a quiz waiting for you on the Teachable platform, if that's where you're watching this video. This is another picture of Simba. So, before we start talking about web pages and web applications and how they are built, I think it's important to do a brief deep dive into the internet itself. What is it, and how does it work? We hopefully at this point understand how pictures, text, videos, and other files can be translated and stored in a given place via encodings like ASCII and UTF-8 and compilers. But how do they actually get sent from one place to the other? The answer is through the internet, which is the global system of interconnected computer networks that uses the Internet Protocol Suite to communicate between networks and devices. So instead of boxes and envelopes, the internet is a method of sending binary information, bits, from one place to another. This picture is the only reference to the matrix I'll be making, but to help visualize, the internet is literally a system of highly complex and interconnected streams of zeros and ones that are traveling from one place to another. But how can ones and zeros get sent? What does that actually mean? So imagine a wire that's connecting two people in different places. When one person flips a switch on one end, the light goes on the other end, since they are connected by a really long wire. So flipping it on is a 1, flipping it off is a 0. In this way, I can send a bit. It's a notification of either an off signal or an on signal, where again, off is 0 and on is 1. So the person on the left flips a switch, or rather the person on the right flips a switch, or either, and the person receiving the message will see the light go either on or off, and they'll know that I either received a 1 if the light goes on, or I've received a 0 if the light goes from on to off. But what if I wanted to send 5 zeros in a row? How does the receiver know how many zeros are in a row if the switch just stays off for a certain amount of time? Was it 1 0 that got sent, or 10 in a row? I really have no way of knowing without some additional information. This is where we introduce the concept of bandwidth. How many bits are sent per second? Now, if the receiver has seen their light has been off for 5 consecutive seconds, and they know to expect a bandwidth of 1 bit per second, they now know that they received 5 consecutive zeros. Alternatively, if their bandwidth was 2 bits per second, they now know that they received 10 consecutive zeros. Bandwidth is a fundamental concept in understanding how data is sent and received. It's measured by the number of bits per second. Another important metric is latency, how much time it takes a single bit to go from point A to point B. So in the example of the light bulb, how long did it take between the time the sender flipped the switch and the time the receiver saw the light go on? This is a very important distinction. How long for a single bit to be sent and received versus how many bits the receiver can process in a given time interval. So now we know that bits can be sent via signals that represent either on or off. But we also know that computers don't have humans sitting on either end looking at light bulbs going on or off. So the next question then becomes, what sort of medium can we use to send messages over that computers can register, with the goal being to maximize bandwidth and minimize latency? I want a given bit to be transferred as fast as possible and as many bits as possible to be sent and received within a given time period. So today, we send binary information via three methods: electricity, light, and radio waves. We're going to dive into each one. When transferring data via electricity, we're talking about copper cables, which in the real world are manifested as coaxial cables, the image on the left, and Ethernet cables, the image in the middle. I'm sure you've already heard of these, or at least seen them in your apartment or plugged into your computer at some point. The benefits of copper cables is that they're cheap. They're just basic copper wires that are ultimately connected to your physical devices. Electrical signals flow from point A to point B, which represent encoded bits of information. So, bits are represented by the current flowing through the wire. Either the current is on or the current is off. So this is similar to the light bulb example. Flipping the switch on turns on the current, flipping it off turns it off. With this, you can create a stream of high current and low current that has encoded binary information in it. The limitation of Ethernet cables, however, is that they have a maximum possible cable length before you start compromising the quality of the signal and the durability of the copper cable. The longer they are, the more likely they are to be affected by interference. Additionally, they have a limit in terms of bandwidth, in terms of how fast electrical pulses can pass through a copper cable. So, if we're talking about sending bits and bytes from America to India, copper cables are not the right solution. They just wouldn't work, since they lose quality over large distances and would corrupt the data that's being sent. So, I want us to visualize these and make sure we understand what sending bits via electrical pulses through copper wire actually means, since the general concepts apply regardless of medium. So let's say you had a message that contained the number 69 and the number 72. That's it. That's the text message. And that message was being sent from one computer to another via a copper cable. What would happen is you would first create a digital signal to encode each number's binary representation. So the number 69 in binary is 010000101, and the number 72 in binary is 01001000. So now your ones get represented by a high 5 volt voltage, and your zeros are represented by a 0 voltage off, low voltage. So you can see the digital signals that each of those numbers produces, and there's two more here, 76 and 80, just as additional examples. But whenever there's a plateau at 5 volts, that's a 1. Whenever there's a drop back down to 0 volts, that's a 0. And finally, at the bottom, you can see how those signals are sent, one after the other, across a copper wire. The computer receives them, puts them back into the decimal human form for the receiver to read, and there you go. Your message has been successfully sent and received. So sent, when it's sent, it's translated into its binary form, which through a digital signal. It's sent across the wire. The receiver receives it, takes that binary representation, puts it back into human readable form, and that shows up on your device. To improve on copper cables, which again experience signal loss over long distances and are capped by the speed at which electrical pulses can pass through copper, what is the fastest thing in the universe that doesn't experience signal loss over long distances? Light. And so that's where fiber optics comes into the picture. Fiber optics cables are long threads of glass engineered to reflect light. We can therefore send a pulse of light through a fiber optics cable to represent either a 0 or a 1. So the particle of light bounces back and forth the length of the cable before reaching its destination at the speed of light. To add even more benefit to this, you can slightly alter the bounce angle for different bits and thus send multiple bits at the same time. So it's not only faster than electricity for a single bit, but you can also parallelize multiple bits being sent at the same time, which improves bandwidth significantly when you compare it to copper cables. Fiber optics is really, really fast. The cons are that it's more expensive since the cables are made of glass, and therefore it's also a little bit harder to work with. That said, since fiber optics does not lose quality over long distances, we use fiber optics cables to support the internet on a global scale. So there are literally massive transatlantic fiber optics cables that run under the sea that connect the world. And the revolutions of fiber optics is how we really connected people on a global scale. These transatlantic submarine cables are laid down by using specially modified ships that carry the submarine cable on board and slowly lay it out onto the seabed as per the plans given by a cable operator. The ships can carry with them up to 2,000 kilometers length worth of cable. And so that image on the bottom there just shows you like a ship moving through the ocean laying down cable. And then the image on the top here shows the network of cables that sit on the ocean floors to connect America to India, India to Indonesia, and so on. So again, two important distinctions here. Instead of maxing out our bandwidth at the speed at which electrical pulses can pass through copper, we're now shifting to the speed of light, which is much, much, much higher. And instead of sending electrons through a copper cable, we're sending photons of light through a glass cable, which also removes most of the interference and signal loss concerns over long distances. Light cannot be corrupted. So fiber optics, better than copper cables, except for cost and maintenance. So that's option number 2. But now let's talk about how we move things without wires or cables at all. Each of us doesn't have a fiber optics cable that we plug directly into our laptop usually, right? That would be expensive and not really convenient at all. So what do most of us use instead? Well, we use Wi-Fi. And Wi-Fi uses radio waves to transfer bits. Radio signals are used to transmit ones and zeros from your router to your physical device, which we commonly know as Wi-Fi. Super convenient and no cables required. But similar to copper cables and electricity, radio signals have the limitation of not having a very large range. They get corrupted and distorted as the distance between 2 points increases. This is the same reason you can't listen to a Los Angeles radio station in New Jersey. But if you have a router in your area that receives bits from the internet via a combination of fiber optics and copper cables, and then forwards those bits to your device via radio waves, then you have a winning combination. And so that's how these three modes of transferring bits are tied together. Fiber optics cables are the biggest piece here. They run across the floor of the ocean and connect the world. After this point, your internet service provider offers either more fiber optics cables, which is a newer phenomenon, or copper cables to connect the internet to your local modem and router. Finally, radio waves then take over and do more of the local connections in a completely wireless manner, connecting your modems and your routers to your physical devices. And thus, you have the internet. So this picture just kind of shows that. On the very left, you have these kind of hub wires, let's call them, and then those then connect directly into your modem. Your modem then connects to your router, and so all of that flow is either via fiber optics cables or copper cables. And then once it hits your router then converts that to radio waves, which are then streamed to your wireless devices. Alternatively, you can also take an Ethernet cord directly into your modem and plug it into your laptop or your desktop. That's just you're bypassing using Wi-Fi and you're connecting straight into your modem. That's also an option. And so that's the internet. More forward-looking, technologies like Starlink are trying to introduce new mediums for the transmission of bits. Starlink in particular is using lasers via satellites. So, a laser of encoded data is sent up to a satellite and then bounced somewhere else to be received. While providing lower bandwidths when compared to fiber optics because nothing travels faster than the speed of light, the game changer here is access. People all over the world, especially in rural areas who otherwise don't have reliable internet because they don't necessarily have the necessary infrastructure, the internet service providers, or cables running into their towns or villages for people to connect to, will now be able to connect to the internet without needing those things. Starlink satellites will beam an internet signal directly to a gateway or a user terminal on the ground, which then users can connect to from the area. That means there's much less infrastructure required and no massive cables to speak of. Instead of cables providing connection on the ground, we'll now use lasers in the sky. So that's a really cool initiative that's being worked on through the SpaceX program. All right, so hopefully now we understand how packets of data can be moved from one place to another. Now, let's shift our focus to the Internet Protocol, which defines the necessary formats of data packets that are sent and received, and provides an addressing system for the Internet. The simplest way to understand the Internet Protocol is to think of the system we use to send physical letters or packages. The system, our postal service and all of its rules, regulations, and standards, including the way we format and address our packages and letters, is analogous to the Internet Protocol. We have the to address, the from address, both of which need to be written in the right place and in the correct format in order to be valid and processed by the USPS. A similar system applies to how devices connected to the Internet are addressed and how data is sent between them. The main takeaway from the Internet Protocol that we're going to cover in this class is that all the different devices on the Internet have unique addresses. This address is just a number, an Internet Protocol address, or an IP address. This is similar to how homes and businesses have mailing addresses. When you're requesting data from a particular IP address, you send a message to that IP address containing your own IP return address and your request, which the recipient then looks at, processes, and replies to with the requested data, back to the originating IP address. We're not going to get into the nitty-gritty of what the various parts of an IP address mean, but just know that at the end of the day, they represent nothing more than a unique address of a given machine. Similar to how no two places in the world can have the same mailing address, no two devices in the world can have the same IP address. Most users of the internet, however, don't really know or care about specific IP addresses, because there's layers built on top of the IP address that are interacted with, as opposed to the actual IP address itself. Think of this as how when we send physical letters and packages, we don't send them to specific latitude or longitude coordinates. Even though those coordinates do technically represent the unique physical addresses of the places in question, we use more human legible formats on top to address our locations. Words like street and drive and circle and way, with house numbers and street names and zip codes. The analogous internet version of this is the domain name system, or DNS, which associates or maps domain names to specific IP addresses. So the DNS might tell you that the domain name of www.google.com maps to the IP address of 111.222.333.444, which is the machine that is the entry point into all of Google's web services and all of its data. That entry machine will then communicate with many other machines, but as a user, you don't really care about that. You just need to know the address of the front door. DNS tells you the address of that front door, and it is distributed. So when you see things like .com or .org or .edu or .net, these are maintained by separate DNS entities. So if you're requesting data from a .net website, the .net DNS will provide you with the corresponding IP address of the .net domain name that you care about. So from the user's end, if a user requests data from www.google.com, the .com DNS provides the IP address for the front door of this website, which then your browser sends a request to for data. I want all the search results for my search string of Jay-Z or Alicia Keys. More on what this request for data actually looks like in the next slide, but all you need to know for now is that every website maps to an IP address that represents its front door, which then your physical device, which also has an IP address, requests data from via the rules of the Internet Protocol. So let's take it one step further then and put it all together. The first step is you visit a website. You open a web browser, you type in the URL, which stands for the Uniform Resource Locator, and hit enter. As we just discussed, your browser then looks up the IP address corresponding to that URL via DNS, and with that in hand, sends a request for data to it through the internet. But what is the content of the message it is sending? How is that message understood by the server you are communicating with? And what is the response it sends back to your web browser and your machine? So this is where we connect back to programming languages. The language that machines use to request and receive data from other machines over the internet is called HTTP, Hypertext Transfer Protocol. HTTPS, for those wondering, is just a wrapper around HTTP that provides additional security guarantees for both your request and your response. The machine that receives the HTTP request will then figure out what it needs to satisfy your request, do that work, generate a reply, and send it back as an HTTP response. So a request made in HTTP looks like the following: get/maps HTTP/1.1 from the host, which is www.google.com. When this request is sent, this tells the Google server that you want all the data associated with the maps page to be returned to your machine to be rendered. The data that is returned to you in the response from the Google server now brings us to a second language, HTML, which is called Hypertext Markup Language, which is what HTTP response contains. HTML is ultimately the language that tells the web browser how to make the page look and feel. The text on a given web page is included in the HTML response from the server, as are the instructions on how to format and style the content, as well as the behavior of the content itself, which we'll get to in a second. Your browser then takes this HTML response and renders the web page that you are requesting, which then you as the user can interact with. So in the case of the previous HTTP request for /maps on google.com, the Google server would return all the HTML associated with the maps page, which then your browser would render for you to look at and interact with. More on that in a bit, but at a high level, that's what's happening whenever you access any website. So to recap the internet then in a very simplistic way, you open your web browser on your device, which has an IP address. Your web browser is your device's portal into the internet. You enter a URL into your web browser and hit enter. The URL is first translated via DNS into the IP address that corresponds to the web server that will respond to your request. Your device then sends a request for data to that IP address via the HTTP language, which the web server understands. The web server does some work and returns an HTTP response to your IP address containing HTML. Your web browser then renders this response, resulting in you viewing and interacting with the web page that you requested. And to reiterate, any communication that occurs between any two IP addresses, including DNS lookups, HTTP requests, and HTML responses, is occurring via zeros and ones that are transferred via machines, via the internet, via either cables, fiber optics or copper, or Wi-Fi. And in a nutshell, that's the internet. So now that we have a general idea of how the internet works, let's take a look at a different cut. And this is where we finally start diving into software development itself, which will continue from now until the end of Class 5. A given website, which is more technically referred to as a web application, has various components and software layers within it. This is true for every website and application in the world. The sum of these various layers is what is referred to as the stack. The simplest and most widely used architecture of the stack, which we will be covering, consists of three layers. The presentation layer, which is what the client sees when they access the application through a website or a web-based application portal. The logic layer, which contains the application logic and business rules that help fulfill application requests. So this layer makes calculations and decisions about how to process requests while controlling the transmission of data between the data layer and the presentation layer. And finally, the data layer is a server-side system that passes information to the logic layer when it is necessary to complete a calculation, or when it needs to be passed to the presentation layer where it becomes visible to users. Each of these layers has unique requirements in terms of the programming languages and software tools that are required to establish and maintain its function. A web-based presentation layer may be written in languages like HTML, JavaScript, and CSS. The application layer could be written in Java, C#, Python, or C++. And applications like MySQL and MongoDB could be used to maintain the back-end database servers. Those things shouldn't mean anything to you yet, but if they do, you're in a good place. If they don't worry. I'm just trying to highlight the different parts of the stack and how they require different knowledge of different tools, programming languages, and concepts. The term software stack refers to the set of components that work together to support the execution of the application. Some software components power back-end processes, some are used to perform calculations, and some are used in the presentation layer to enable user interaction. In any case, the components of a software stack work in tandem to efficiently deliver application services to the end user. So, each web application has its own stack, which is built by its own team of engineers. You can have simple stacks, complex stacks, stacks that only have a presentation layer, stacks that have a massively complicated logic layer and a minimal presentation layer. You can take your pick. For this class, let's use an example or an app that we're probably all familiar with at this point, Airbnb. In Airbnb, the presentation would again be all the things you see and interact with when you click through the application. On any page, there's the text, the styling, the visual interactions that take place when you click on different buttons, parts of the map, etc. This is all the presentation layer, also known as the front end, which is what we'll be covering in this class. The logic layer would comprise of all the algorithms and business logic associated with the Airbnb application. How are search results filtered based on the criteria you provide as input into the application? How are listings sorted by relevance on the results page when you search for places to stay? How are experiences connected to given listings? How are hosts validated and verified before they can become superhosts or even onboarded more generally? All those processes live inside the logic layer. The output of those processes are injected into the presentation layer to be rendered. Finally, the data layer would comprise of all the databases that the application depends on. Where are all the listings stored? Where are all the hosts stored? Where are all the users stored? Each of these has a database that the logic layer interacts with before that logic layer runs the processes that ultimately generates the final HTML that is returned as part of the presentation layer. The process of developing an application like Airbnb can be broadly divided into two components: front-end development, which captures the presentation layer, and back-end development, which captures the logic layer and the data layer. Each of these represents a specialization among developers, although nowadays full-stack developers are capable of doing both. For this class, we're going to focus on the presentation layer, aka the front end. So let's dive in. Again, just to reiterate, the front end of an application is basically synonymous with the presentation layer. Front-end developers focus on the client side of the application, aka what users actually interact with, creating visually appealing and user-friendly interfaces that are easy to navigate and properly connected to back-end systems, or the server side of the application. At its most fundamental level, the code associated with the front end can be broken down into three components: HTML, CSS, and JavaScript. And thus, these are the most commonly used programming languages for front-end developers. HTML, the language that is ultimately contained in the HTTP response that is returned by the web server and rendered by the web browser, is the programming language that captures and encodes the structure and content of the web application. CSS, which stands for Cascading Style Sheets, is the programming language that encodes the style and aesthetic features of the content of the web application. Everything from font color to placement to the width and height of a specific section of the page, all of this is captured by CSS. JavaScript dictates how the content of the web application behaves or is interacted with. It allows you to implement complex features on web pages. Every time a web page does more than just sit there and display static information for you to look at, displaying timely content updates, interactive maps, animated 3D graphics, scrolling lyrics, etc. You can bet that JavaScript is probably involved. I always like to visualize these as HTML accounts for the nouns or the content of your application, CSS for the adjectives or the descriptors of your web application, and JavaScript for the verbs or the actions of your applications. So let's dive into each one. So as we just mentioned, HTML is the content itself. HTML stands for Hypertext Markup Language, and it gives content structure and meaning by defining that content as, for example, headings, paragraphs, or images. When you get started with HTML, you will likely encounter new and often strange terms. Over time, you'll become more and more familiar with all of them, but the two common HTML terms you should begin with are elements and tags. Elements are designators that define the structure and content of objects within an application. Some of the more frequently used elements include headers, paragraphs, images, and titles. The use of less than and greater than angle brackets surrounding an element creates what is known as a tag. Tags most commonly occur in pairs of opening and closing tags. An opening tag marks the beginning of an element. It consists of a less than sign, followed by the element's name, and then ends with a greater than sign. A closing tag marks the end of an element. It consists of a less than sign, followed by a / and the element's name, and then ends with a greater than sign. The content that falls between the opening and closing tags is the content of that element. A paragraph element, for example, will have an opening tag of less than p greater than, and a closing tag of less than / p greater than. What falls between these two tags will be the content of the p, which is the paragraph. Let's visualize this. So here you can see a given element and the tags that enclose it. What's highlighted in green are the tags. The opening tag consists of an opening bracket, the name of the element, and a closing bracket. Then comes the content of the element, and then the closing tag, which consists of an opening bracket and a /, the name of the element again, and a closing bracket. Below the generic format, you can see an actual example. Here, an H1 element, which is a header with the content of Black Goose Bistro, is created. Let's go further and look at another example. In this HTML snippet in the top of the page, we have coded 3 elements: a header, a paragraph, and a button. You can see the opening and closing tags for each, as well as the content for each. In the second image, you can see how the web browser would render these elements if that exact block of HTML above were returned in an HTTP response. So you hit www.testwebsite.com, and the HTML response is what is above. Your internet browser would show what is shown here in the bottom image. So that's raw HTML. And again, ignore the color of this text and JavaScript notes as the content, since we haven't actually added those yet. Now we get to our adjectives via CSS, which dictates how the HTML is decorated. So again, CSS allows us to add layout and design to our pages, and it allows us to share those styles from element to element and page to page. The word cascading comes from the specified priority scheme to determine which style rule applies if more than one rule matches a particular element, which we'll get to. When a browser displays a web page, it must combine the web page's content, the HTML, and its styling information, its CSS, to produce a final visual rendering. It processes this information in a number of stages, which we're not getting into. But basically just remember that the content, the HTML, and the CSS, the styling guide, go hand in hand. The separation of formatting and content makes it possible to present the same page content in different styles for different rendering methods. So think about mobile versus web. You can take the same HTML, the content, and attach different styling sheets to it based on whether that content is being requested from a laptop or from a phone. Let's look at the example from earlier, except now let's include a CSS file. In this CSS file, on the left, you can see that there are blocks of definitions. This sheet is saying that for anything in the HTML code that is a header tag, we are going to make the font bold and give it some margin underneath. That's what that first block is, lines 1 through 5. For any paragraph tag in the HTML, that's lines 7 through 10, we're going to say the color of the text should be tomato red, and we're going to add some margin below the paragraph. And for any button tag in the HTML, that's lines 12 through 21, we're saying the button text should be white, the background color should be Dodger blue, there should be a solid navy colored outline around the button, along with a few other things. The combination of the HTML from the previous slide and the CSS shown here results in a web page that is rendered like the image on the bottom right. So now if your HTTP response contains not just the HTML, but the CSS as well, your web browser would render it with the colors and the styling that you specified in your CSS sheet. Finally, we get to JavaScript, which dictates how the content behaves or is interacted with, our verbs. JavaScript is a programming language that allows you to implement complex features on web pages. Every time a web page does more than just to sit there and display static and information for you to look at, reacting to events, displaying timely content updates, interacting with dynamic maps, animated graphics, scrolling lyric videos, the list goes on. Anytime something like that is involved, you can be guaranteed that JavaScript is also involved. It is the third layer of the layer cake that constitutes the front end, the two other layers being HTML and CSS, which we just covered. The JavaScript language consists of some common programming features that allow you to do things like run operations on pieces of content, run code in response to certain events occurring on a web page, and much, much more. So let's keep looking at the same example from earlier, except now let's also include a JavaScript block. Now, when this JavaScript block is also contained in the HTTP response, which says that when a button is clicked, we want to change the opacity of the paragraph element to 0. In other words, when the button is clicked, we want to make the paragraph disappear. So when this JavaScript block is joined to the HTML and the CSS and the button is clicked, the page will be rendered like it is in the two images on the bottom. Initially, it'll be just as it was before with just the HTML and the CSS. But the difference is that now the button we have made interactable. So when the button is clicked, there will be an event in the response to that click, which will make the paragraph disappear. So again, we've tied an action now to the HTML content via JavaScript. So those are the three foundational elements of front-end development: your nouns, your adjectives, and your verbs. But let's take a look at what else it means to be a high-functioning front-end developer. Front-end developers are responsible for a website's user-facing code and the architecture of its immersive user experiences. In order to execute those objectives, front-end developers must obviously be adept at the three main front-end languages: HTML, CSS, and JavaScript. In addition to fluency in these languages, however, front-end developers need to also be familiar with front-end frameworks and libraries like Bootstrap UI, Material UI, React.js, Node.js, or AngularJS. What these frameworks and libraries do is they package CSS and JavaScript code into distinct and predefined UI components and behaviors that you can then plug into your application without needing to build everything from scratch each time. So let's say your application needs an interactive table that displays, filters, and sorts information. Instead of writing your own HTML, CSS, and JavaScript for this table from scratch, you can just import the React.js library and inject a pre-made React.js table into your page. Oftentimes, companies that have built clean and reusable components and behaviors that they are proud of will publish them as open source material for others to adopt. In doing so, they both contribute to the wider development community and build upon their branding and stylistic visions for the wider internet. For example, React.js is built and maintained by Facebook, and Bootstrap is built and maintained by Twitter. There are also libraries like jQuery, which focus less on predefined UI components and behaviors and more on packaging JavaScript code into a more concise, time-saving form. This makes JavaScript programming more intuitive and efficient. And jQuery is a common library that front-end developers should have some experience with. Using these additional frameworks and libraries, along with the foundational languages we discussed, front-end developers work closely with designers or user experience analysts to bring mock-ups from development to delivery. Front-end developers often can say about themselves, "I'm a technical person, but I'm still a visual person," which makes it a position with a lot of responsibility, but it can be very, very rewarding. At the end of the day, a front-end developer is responsible for the interior and exterior design of a car, whose engine and inner mechanic structure is represented by the backend, which we'll get to in the next class. They control the taste and style of the decor, and thus front-end developers are often excited about what they do because they're really able to leverage their creativity. So, using these three programming languages, HTML, CSS, and JavaScript, as well as the open source libraries and frameworks that exist in the ecosystem, you can theoretically build any web page. But you don't want to just build any web page. You want to build web pages and features that follow industry standards and that customers actually want to use and interact with when they land on it. This leads us into the world of design, which gets us more into the art and creativity side of front-end development. Before we jump into specific design topics, I want to go over the difference between UI and UX, which is a common open question in the land of software development. User interface, UI, is the specific assets that users interact with. It deals with traditional concepts of visual design elements. Thinking about ordering food online for pickup delivery as an example, UI would focus on the visual design of the screens a user interacts with, such as which color to make the order button and where to place it on the page. This can also include any interfaces a user might come in contact with in-store. User experience, UX, on the other hand, is the interaction and experience users have with a company's products and services. UX design uses a process called design thinking to understand the customer journey and develop the right product. This process starts with a problem and ends with a wireframe or a prototype. So again, thinking about ordering food online for a pickup delivery, the UX consists of the user's interactions with placing their order on a company's website, their in-store experience of picking up their order, and their satisfaction with their food. UX design is about understanding the overall journey of your users and turning it into a product. UX as a category is not necessarily tied to websites. So, to cover UI design at a high level first, we're going to take a look at some common fundamental visual design patterns. After that, we're going to cover UX at a high level by going over the process of design thinking. I want to caveat this part of the class with, I am not a designer. I have done front-end development when necessary, but what follows is very much beginner's material in the world of design. Design is a very nuanced discipline, so if it interests you, please do more research and find some more literature on the subject or people in the design world who have walked the walk as their own career. There's a lot of content out there, as well as a lot of really talented people. So let's jump into UI design. One of the core philosophies of UI design is that even if you know what product you want, you just don't want to build anything. You want to build web pages and features that follow industry standards and, more importantly, that customers actually interact with when they land on them. Some random quotes to get us started here. One's from Steve Jobs. He said, "Design is not just what it looks like and feels like. Design is how it works." And the next one, users spend most of their time on other sites that are not yours. This means that users prefer your site to work the same way as all the other sites they already know. So this is just a way of saying that consistency across applications on the internet is very important as well, not just within your application as a standalone unit. So with that said, let's jump into some fundamental philosophies of good design, and then go over 9 important principles of web design to help get a feel for what matters. An effective website design should fulfill its intended function by conveying its particular message while simultaneously engaging the visitor. When designing a website, there are many key factors that will contribute to how it's perceived. Several factors such as consistency, colors, typography, imagery, simplicity, and functionality all contribute to good website design. Ultimately, though, a well-designed website can help build trust and guide visitors to take action. One aspect of a great user experience involves making sure your website design is optimized for usability, form and aesthetics, and how easy it is to use, functionality. So this is where you can start to see how UI and UX are interconnected. Good UX depends on good UI and vice versa. So let's talk about some fundamental design patterns that are commonly used across all web pages and applications.
So number 1, website purpose. This one's a pretty obvious one, but your website or application should have a clear intention on each page that it contains. This will help the user interact with what you have to offer. Do not leave room for ambiguity. What's the purpose of your website? Are you imparting practical information like a how-to guide for your cool woodworking project? Is it an entertainment website like sports coverage of your favorite athlete? Or are you selling a product to the user like fun necklaces made from precious stones? There are many different purposes that websites may have, so make sure the purpose of your website is pretty immediately clear to your users. If the user lands on your application or website and doesn't really get what it's for pretty immediately, you're doing something wrong. Additionally, make sure the purpose of each individual page within your website is also pretty immediately clear. The About Us page, the Cart page, the Your Account page, etc. Number 2 is simplicity. Simplicity is the best way to go when considering the user experience and usability of your website. Some ways to achieve simplicity through visual design are through factors such as color. Color has the power to communicate messages and evoke emotional responses. Finding a color palette that fits your brand will allow you to influence your customers' behavior towards your brand. Keep the color selection limited to less than 3 colors. I've been advised that complementary, soft colors usually work very well. a soft green with a soft purple, for example. Pleasing color combinations increase customer engagement and make the user feel good when they're interacting with your product. Typography has an important role to play on your website as well. It commands attention and works as the visual interpretation of the brand's voice. Typefaces should be legible, and you should only use a maximum of 3 different fonts on the website. Imagery is every visual aspect used within communications. This includes still photography, illustrations, videos, and all forms of graphics. All imagery should be expressive and capture the spirit of the company and act as the embodiment of their brand personality, but it shouldn't be too in your face either. That said, most of the initial information we consume on websites is visual, and so whatever imagery you do use as a first impression, it's important that high-quality images are used to form an impression of professionalism and credibility in the visitor's mind. Don't use blurry images, unless of course the art in doing so is intentional. Number 3 is navigation. Navigation is the wayfinding system used on websites where visitors interact and find what they are looking for. Website navigation is key to retaining visitors. If the website's navigation is confusing, visitors will give up and find what they need somewhere else. Keeping navigation simple, intuitive, and consistent on every page is key. You don't want people getting lost and losing their way. The image on the right here shows the industry standard of a navigation menu, known colloquially as the hamburger bun icon. Use it. Number 4 is an F-shaped pattern of reading. The F-shaped pattern is the most common way visitors scan text on a website. Eye tracking studies have found that most of what people see is in the top and left area of the screen. The F-shaped layout mimics our natural pattern of reading, at least in the West, left to right and top to bottom. An effectively designed website will work with the reader's natural pattern of scanning the page. 4 quick ones. 1 is visual hierarchy. Visual hierarchy is the arrangement of elements in order of importance. This is done either by size, color, imagery, contrast, typographically, with white space, texture, or style. One of the most important functions of visual hierarchy is to establish a focal point. This shows visitors where the most important information is. 6 is content. An effective web design has both great design and great content. Using compelling language, great content can attract and influence visitors and convert them into customers. Load time. Waiting for a website to load will lose visitors. Nearly half of web visitors expect a site to load in 2 seconds or less, and they'll potentially leave a site that isn't loaded within 3 seconds. Optimizing image sizes will help you load your site faster. Mobile friendly. More people are using their phones or other devices to browse the web. It's important to consider building your website with a responsive layout where your website can adjust to different screens. So if someone's looking at it on their phone, their tablet, their laptop, their massive TV screen, it should be user-friendly and visible across those mediums. And finally, a grid-based layout. Grids help to structure your design and keep your content organized. The grid helps to align elements on the page and keep it clean. The grid-based layout arranges content into a clean, rigid structure with columns, sections that line up and feel balanced. This results in an aesthetically pleasing website. The 2 images here you can kind of see the 2 different ways to implement the grid-based layout, and there's many others out there that are not shown in these images. All in all, these principles are a good place to start, but make no mistake, the world of design is complicated and constantly changing. As someone who spent nearly a decade learning how to design and build web apps, I still know very little about it. It's important to find the right people who know what they're doing to take a product vision and transform it into a user interface that customers actually want to use. The talent pool isn't very large, but there are definitely very talented people out there for the job. So, design patterns are what makes your web page or application attractive, functional, and usable. They provide you with helpful guidelines when you're building your user interface. But how do you actually ensure you're building the right thing for the problem you're trying to address? How do you actually design your product itself in the right way so that users have a positive experience with it? This is less about how pages look, but more about what pages you have, and more about whether those pages serve the function you're envisioning or the function that your customer actually needs. This gets us into the world of design thinking. So first off, what is design thinking? Design thinking is a non-linear, iterative process that teams use to understand users, challenge assumptions,
redefine problems, and create innovative solutions to prototype and test. Why is it important? In user experience, UX, it's crucial to develop and refine skills to understand and address rapid changes in users' environments and behaviors. The world has become an increasingly interconnected and complex place. 21st century organizations from a wide range of industries find design thinking a valuable means to problem solve for the users of their products and services. Design teams use design thinking to tackle ill-defined or unknown problems because they can reframe them in human-centric ways and focus on what's most important for their users. Of all design processes, design thinking is almost certainly the best for thinking outside the box. With it, teams can do better UX research, prototyping, and usability testing to uncover new ways to meet users' demands. Design thinking's value as a driving force in business, global heavyweights such as Google, Apple, and Airbnb have wielded it to notable effect, matches its status as a popular subject at leading international universities and business schools. With design thinking, teams have the freedom to generate the right solutions for the right problems. Using it, teams can uncover hard-to-access insight and apply a collection of hands-on methods to help find innovative answers. So the Hasso-Plattner Institute of Design at Stanford, aka the D School, describes design thinking as a 5-stage process: empathize, define, ideate, prototype, and test. And so we're going to dive into each of these phases here. Empathize is the first stage of the design thinking process, in which design teams conduct research to get personal grasp of their users' needs. They set aside assumptions to obtain insights into the user's world by observing and consulting with them. This way, they can actually understand users' experiences, motivations, and problems. Empathize is design thinking's first stage for a reason. It's the first step on the road to thoughtfully design products that prove the designer is built with a compassionate eye for their users. Empathy is a naturally occurring characteristic which people have in varying degrees based on the sum of their life experiences. However, anyone can improve their ability to empathize as a soft skill. Anyone in a design team will have preconceived ideas about the many situations people find themselves in as users. It's unavoidable. You can't unlearn your own life experiences. But these preconceived notions are the exact thing designers need to see past in order to do their jobs effectively. Therefore, you should always adopt a beginner's mindset to be able to view and analyze situations with users objectively. Assume you know nothing. To empathize, then, is to research. You should constantly remind yourself to question everything you observe instead of judging. You should listen to others open-mindedly rather than focus on points that confirm your own biases, because our biases will naturally creep into how we view the world and the situations we consider. As designers, or design thinkers, we must catch and overcome these before they distort our research. You must become fully objective before you can start to see through your users' eyes and interpret their viewpoints optimally. The users are the only experts on their own needs and desires. The ultimate goal of this stage of the process is to understand the user's dimensions of use, aka the tasks that they perform, and their feelings, their motivations for performing those tasks, before you can work towards delighting them through your own product design. If you don't know what they really need, you can't give them what they really want. Pretty simple philosophy, very broadly applicable. So how does one empathize practically to get the insights needed? You have a range of options, all of which involve actual interactions with potential users. These include observing real users and asking questions. What? You're detailing your observations. How? You're analyzing how users are actually doing things with difficulty or with ease. And why? You're making educated guesses about the user's emotions and motivations. You can also interview users directly. Your team uses brainstorming to first find the right questions to ask in a generally structured and natural flow. Then, you can directly ask users for their insights in an intimate setting where they can respond earnestly to open-ended questions. You can engage with extreme users. You find the extreme cases within your user base to determine the greatest degree of users' needs, problems, and problem-solving methods. You can then see the full scope of problems which typical non-extreme users might run into. If you can satisfy an extreme user, you can satisfy any user. You can conduct photo and or video-based studies in users' natural environments or sessions with the design team or consultants. You record these users while they try to solve an issue you propose to resolve with your design. You can use personas to establish accurate portraits and profiles of users who will interact with your product. And you can share inspiring stories. Your team can share stories about what they have observed, so you can draw meaning from these and note the interesting details as a larger group. So again, going back to the food ordering example, at this stage you really want to be observing with how people currently eat their meals, right? How many meals per week do they eat at home? How many times do they order food? When they order, do they use the phone to call in? If so, why? Is it because they're old school or because they hate the website? If the latter, what about it do they hate? What could cause them to not hate it? What is the age distribution among the percentage of meals ordered for delivery/pickup and among ordering via the phone/website? Among the people who order online, what is their exact process for ordering? Do they know what they want already, or do they need an online menu as well? Do they pay with card or Apple Pay or cash? All these are fair questions to ask when gathering insights into the problem that you're trying to solve. Whichever approach or approaches you take, beware of formulating solutions at this stage. Aim to realistically envision possible scenarios where users experience problems. Empathize is not just a key part of design thinking, it's also pivotal to user-centered design and user experience design. When your design team remains aware of your users' realities and remains passionate about helping real people solve real problems, you'll reap precious insights which you can ultimately translate into products that your users will love. The next step in the process is to define, to state your users' needs and problems. This step entails accumulating the information you gathered during the empathize step, analyzing the observations, and synthesizing them into problem statements. A great definition of your problem statement will guide you and your team's work and kickstart the ideation process, which is the third stage, in the right direction. On the contrary, if you don't pay enough attention to defining your problem, you'll work like a person stumbling in the dark. This is perhaps the most challenging part of the design thinking process. So what makes a good problem statement? Well, it should be 1. Human-centered. It requires you to frame your problem statement according to specific users, their needs, and the insights that your team has gained in the empathize phase. The problem statement should be about the people the team is trying to help, rather than focusing on technology, monetary returns, or product specifications. Your problem statement should be broad enough for creative freedom, which means that the problem statement should not focus too narrowly on a specific method regarding the implementation of the solution. The problem statement should also not list technical requirements, as this would unnecessarily restrict the team and prevent them from exploring areas that might bring unexpected value and insight into the project. Your problem statement should also be narrow enough to make it manageable. So a problem statement to, quote, improve the human condition is too broad and will likely cause team members to easily feel daunted. Problem statements should have sufficient constraints to make the project manageable. A point of view, POV, is a meaningful and actionable problem statement which will allow you to ideate in a goal-oriented manner. Your POV should capture your design vision by defining the right challenge to address in the ideation sessions. A POV involves reframing a design challenge into an actionable problem statement. You articulate a POV by combining your knowledge about the user you are designing for, his or her needs, and the insights which you've come to know in your research or your empathize mode. Your POV should be an actionable problem statement that will drive the rest of your design work. So POV combines these three elements: a user, a need, and an insight. You can articulate your POV by inserting your information about your user, the needs, and your insights in the following sentence structure. User, you describe the user, needs, what they need, because of the insights that you've gained. And that becomes your POV statement. So here's an example of that. Here we have a user who is an adult person who lives in a city. Their need is to use a car for 10 to 60 minute week trips 1 to 4 times per week. And their insight is that the user doesn't want to own his own car, as it would be too expensive compared to his needs. He would like to share a car with others who have similar needs. However, there are no easy and affordable solutions for him. It's important for the user to think and live green and to not own more than he truly needs. So in this case, we've identified a user, we've identified that user's needs, and we've identified why those are his needs.
And this use case is very relevant to me right now. I live in Brooklyn and I have a car, and I feel a bit torn about it. So when you've defined your design challenge in a POV, you can then start using it by asking a specific question, starting with how might we, or in what ways might we. How might we questions are questions that have potential to spark ideation sessions such as brainstorms. They should be broad enough for a wide range of solutions, but narrow enough that specific solutions can be created for them. Again, how might we questions should be based on the observations you've gathered in the empathize stage of the design thinking process. As another example, you have observed in a POV that Gen Z kids tend to not watch TV anymore because they view the sensationalist media apparatus as blatantly misleading and commercials to be a capitalist nightmare that brainwash them into consuming products they don't really need to continue lining the pockets of rich people who don't actually care about their well-being at all. You realize that the Gen Z youth want other mediums to consume content that are more in line with their societal values and expectations. Some questions which can guide and spark your ideation session could be, how might we create a content streaming platform that filters out misleading or untrue content? How might we create a content streaming platform that requires marketers to demonstrate a societal good before being able to advertise on that platform? How might we make content consumption more social so that young folks feel more engaged and less targeted? The how might we questions open up to ideation sessions where you explore ideas which can help you solve your design challenge in an innovative way. And thus, TikTok was born. More seriously though, the two main outputs of the design stage of the define stage are a POV problem statement and the associated how might we questions that will lead us into our next step, which is ideation. So the next step is to ideate. This is the fun one, where you get to use a lot of sticky notes and just generate ideas and challenge assumptions. The solid background of knowledge from the first two phases means you can start to think outside the box to look for alternative ways to view the problem and identify innovative solutions to the problem statement you've created, which is the ultimate goal of this stage. Brainstorming is part of design thinking and is more of a formal process than the general use of the word that we're used to. It's extremely popular for design teams because they can expand in all directions. Although teams should have rules and a facilitator to keep them on track, they should also be free to use out-of-the-box and lateral thinking to seek the most effective solutions to any design problem. By brainstorming, they can come up with a vast number of approaches. The more, the better, instead of just exploring conventional means and running into the associated obstacles. When teams work in a judgment-free atmosphere to find the real dimensions of a problem, they're more likely to produce rough answers, which they'll refine into possible solutions later. No idea at this stage is a dumb idea. In brainstorming, we aim squarely at a design problem and produce an arsenal of potential solutions. By not only harvesting our own ideas, but also considering and building on those of our colleagues, we cover the problem from every angle that we can. But what is brainstorming actually? It may seem to lack constraints, but it actually involves 8 house rules and having someone act as a facilitator. The rules are: 1. Set a time limit. Depending on the problem's complexity, 15 to 60 minutes is usually normal. 2 is begin with a target problem/brief. Members should approach this sharply defined question, plan, or goal, and remember to stay on topic. 3 is refrain from judgment or criticism. No one should be negative, including through body language, about any idea. 4. Encourage weird and wacky ideas. Further to the ban on killer phrases like too expensive. Keep the floodgates open so everyone feels free to blurt out ideas, provided they're at least tangentially on topic. 5 is aim for quantity. Remember, quantity breeds quality. The sifting and sorting process comes later. 6 is build on others' ideas. It's a process of association where members expand on others' notions and reach new insights, allowing these ideas to trigger their own. Say and rather than discourage with but to get ideas closer to the problem. Stay visual. Diagrams and post-its help bring ideas to life and help others see things in different ways. And 8, allow one conversation at a time. To arrive at concrete results, it's essential to keep on track this way and show respect for everyone's ideas. And then finally, one person should also be scribe to capture the ideas that are being generated and put it on the board or whatever else that you're using to actually track.
The next step, once you've gotten all your ideas out on an ideation board, is to prototype. To establish champions and smaller teams to take the most prominent ideas from the ideation step, you can vote on them or just the ones that naturally come out as leaders from open discussion, and actually build out concepts of what these ideas would manifest as. The aim now is to identify the best possible solution for the problem. The smaller team should produce some inexpensive, scaled-down versions of the product or specific features found within the product to investigate the ideas you've generated. This could involve something called paper prototyping. Paper prototyping might sound silly, but it's a core activity in the design process. You depict screenshots in what you can call paper shots to help determine how your design/product should actually look. If you use it early on, you can prevent unwanted development costs. As you proceed, you can do guerrilla testing to informally test ideas with potential users and course correct as needed. So here's what paper prototyping might look like. You're actually drawing out what your app or feature would look like and how it would flow, mimicking the screens that it will be consumed in. Alternatively, using applications like Figma to create prototypes through software is also an option. The last step in the process is to test your prototypes, to actually try out your solutions. Evaluators, potential users, and teammates rigorously test the prototypes by hammering them with questions and trying to poke holes in them. Remember that although this is the final phase, design thinking is iterative. Teams often use the results of testing to redefine the problem, so you can return to previous stages to make further iterations, alterations, and refinements, to find or rule out alternative solutions. Once you're done with this entire process, your team should have a full prototype of the application or feature you're trying to build, ready to actually be built. You should have a product that your team feels good about and that is ready to be converted into an actual, tangible product. Using this prototype, you can move on to working with your designers to come up with actual wireframes and mock-ups to represent the UI of this product, as well as working with your technical leaders to develop product requirements to be passed on to the engineering team to build. These two things, wireframes and mockups, and product requirements, are essential in the software development process, but we'll touch more on this in Class 5. For now, just be aware that this process is available to you to take a problem that you have and translate it into a visual prototype and attach product requirements that are ready to be built. So again, here are the 5 stages of the design thinking process. Empathize, define, ideate, prototype, and test. And you can see how it's not just a single pass. You can go from test all the way back to define. You can go from prototype back to ideate. You can keep iterating on these steps until you feel like you're actually ready to build what is being proposed. There's a really cool story about how in 2009, when Airbnb first launched, it was on the verge of going under. The company's revenue was flatlined at $200 per week. Split between 3 young founders living in San Francisco. This meant a lot of losses on zero growth. And so one afternoon, the team was poring over their search results for New York City listings with the founder of Y Combinator, trying to figure out what wasn't working, why they weren't growing. After spending some time on the site using the product as a customer, someone had a realization. Quote, "We noticed the pattern. There's some similarity between all 40 of these listings. The similarity is that the photos sucked. The photos were not great photos. People were using their camera phones or using their images from classified sites. It actually wasn't a surprise that people weren't booking rooms because you couldn't even really see what it is you were paying for." So as the story goes, the Y Combinator guy tossed out a completely non-scalable and non-technical solution to the problem. Travel to New York, rent a camera, spend some time with customers listing properties, and replace the amateur photography with beautiful high-res pictures. The 3-man team grabbed the next flight to New York and upgraded the amateur photos they had linked to the images that they then took. A week later, the results were already coming in. Improving the pictures doubled the weekly revenue to $400 per week. This was the first financial improvement that the company had seen in over 8 months. And so they knew that they were onto something. So while this doesn't illustrate a formal instance of the design thinking process to design an app, it does involve all the steps quite organically. Empathize with the customer's experience by using the product as a customer, finding a pattern and defining a problem of poor quality images, throwing out a random idea of literally traveling to New York to take better pictures on behalf of the hosts, prototyping it on a handful of identified listings, and then testing to see if the revenue turned around. Another design thinking success story, the Uber Eats team has something called the Walkabout program, which forms the foundation of their immersion initiatives. Every quarter, designers visit an Uber Eats city and dive deeply into that market. They learn the city's food culture. They study the transportation and logistical infrastructures. They interview delivery partners, restaurant workers, and consumers. They eat and eat and eat, which sounds like quite an awesome job. Upon return, they share their learnings with the entire team. Each visit helps build a comprehensive understanding of the different markets and customers, which in turn translates to how the Uber Eats product continues to evolve in terms of the features that it offers, the restaurants it markets, and so on. They also use order shadowing to allow them to observe their designs in use. They follow partners on their delivery runs, visit restaurants during the rush hours, and sit in people's homes while they order dinner. Watching their products in the wild helps them better understand the needs of their customers, how well their designs addresses those needs, and what challenges exist in the real world that they can't really replicate in the office. All this to say, while the design thinking process might seem cumbersome at first, it's an amazing way to validate that you're building the right thing, not just anything. Identifying what customers actually need by truly understanding their pain points, how they actually use products, defining their problems, creating open-ended questions to answer to address these problems, ideating to prioritize quantity over quality to get everything on the table, and then focusing on a few of the ideas that seem to resonate with the team and actually prototyping them out, and then testing those ideas to see if they hold up, it works. Once you've done all those things, you can really feel confident in the thing you're building, rather than just building something and hoping for the best. And that's it for class number 2. To recap, we first learned about the internet. How are zeros and ones sent from one place to the other, and what languages are used to communicate between machines and to render web pages. We then defined the stack. We defined the various layers of a given web page, the presentation layer, the logic layer, and the data layer, and spoke briefly about what each layer entails. We then jumped into the presentation layer, otherwise known as the front end, covering the 3 main programming languages that are part of this layer, HTML, CSS, and JavaScript, and their purpose. We also covered some of the relevant libraries and frameworks that are often part of a front-end developer's toolkit. We then jumped into the world of design, first covering some fundamental design patterns for any given web page, which are helpful in determining the look and feel of your website that make your application attractive and usable. And finally, we learned about the design thinking process. How do you actually ensure you're building the right thing for the problem you're trying to solve? This was less about how pages look and more about whether they serve the function you're envisioning or that your customers actually need. Next class, we'll be continuing our deep dive into the stack, going to get to the more complex part of it, which is the back end. This includes everything from what are databases to concepts related to information security. So I'm looking forward to it, and until then, have a great day.